Pick. We're going to talk about closure. We're going to talk about closure under these five operations. We're going to kind of lightly prove these five things, and I'm going to show you kind of something constructive that you can do towards the end. In order to do that, I think it makes sense for us to revisit exactly what we mean by a language, talk about closure by stepping away from kind of theory of computation names for a second, and then make our way back. So a language is just any set of strings. It can include the empty string, but any group of strings that you put together inside a set is a language. So a language could have a finite number of components, like the one that you see up here first. We call this one. Let's call this L4. Okay, L4 might have three elements in it: an empty string, a zero, and a one. The language could be infinite, like L5 here. It could have the empty string and then some other kind of sequence. We have seen languages that do things like list all of the strings that are divisible by three. Um, any any list of strings that you can come up with is a language. One such language is the language of all integers. I'm going to use all possible numbers here and not try to push this into binary as we first make this discussion. And so integers is just a set of strings, right? So we could call this a language. And if you don't remember integers, hopefully you're okay with this. One thing that we might say is that, hey, whenever I add two elements from this set together, it seems like I always end up with some other element of the set, right? Anytime I add an integer to another integer, I always end up with another integer. And this is the property of closure. And what we would say in this instance is that integers are closed under addition. It doesn't matter which two integers you happen to kind of list and think about. As soon as you add them together, you end up with another integer. And there's nothing weird or special that you can do to break this rule. And I'm not going to try to prove this to you. For now, I just want you to kind of get used to the idea of closure. And so we would say integers, the set of integers, the set of strings that are integers, we would say integers are closed under addition. Anything we do with an integer and addition, it nets us another integer. Now, the reason integers are often used here is because they are not closed under division. Okay, so let me scroll up here. And you can see here that I've listed 3 or 4 examples of division with integers. And I'm not talking about ints in C++ because those might actually be closed under division. I'm talking about normal arithmetic. 4 divided by 2 is 3. 6 divided by 2 is 3. Sorry, 4 divided by 2 is 2. 7 divided by 2 is 3.5. 1 divided by 3 is 0.3 repeating. Either way, what we see is that if we take two elements out of the set and we divide them, we may or we may not end up with another element in the set. If we take two integers and divide them, we might not end up with an integer. And so we would say integers are not closed under division. And we only need to find one counterexample in order to prove that that is the case. When we want to come up here and prove that integers are closed under addition, we would have to prove it for all integers. That can be pretty hard. But regular languages are actually a little easier, and I'm going to sketch kind of the construction proof for a few of these. So let's assume we have two languages, L1 and L2, and let's also assume that they're regular. Two regular languages, L1 and L2. I don't know what they are. They're just regular languages. That's all I know. If L1 is a regular language, then there is some finite automata that describes it. Okay, and I'm just reading kind of what I've written here. If L1 is regular, then there's a finite automata that describes it. That finite automata that describes it, let's call it machine 1. If language 2 is regular, then there's some finite automata that describes it. Let's call that machine M2. So these machines here, they've got some start state. They might have some accept states in them. You know, they're just cool machines. We don't know what they look like because we're talking about these languages kind of in the abstract. Maybe they have a couple of accept states. Maybe they don't have any accept states. We don't know. But whatever the languages are, they accept some set of strings. It could be the empty set, meaning they don't actually accept anything, but they exist. Now, what I want to do is kind of prove to you that no matter what regular languages they are, I know that the union of them is regular. And if you're struggling a little bit with union, it means the language that consists of any string that could come from either of the first two languages, right? So if the first language is 0, 1 and the second language is 0, 0, 1, 1, then the union of them is all of these strings 0, 1, 0, 0, and 1, 1, right? So if we union these together, we get this. So anything that could come out of either of them. Now, how am I going to prove this? I'm going to prove this by constructing a new machine. I'll call it M3. And the language of this new machine is going to be precisely this union. And this is a rough sketch of how we would prove this. So how do I make this new machine? I'm going to make a new start state. It's going to have empty string transitions to these old start states. And this is exactly how I can put two regular languages together in order to craft a new language that is the union of the two. This can be extremely useful when you're trying to construct finite automata for yourself. And while this is just a property of regular languages, this is a useful property in the sense that it teaches us how to make other languages using smaller components. Um, so anytime you find yourself stuck, maybe if you can find a way that you can say, well, the language I want to build is the union of these two other languages, that would be great. Often you can think of that as or, sentences with the word or. So maybe it's my strings come from this language or this language, right? It's an or kind of statement. It's kind of like the plus and the regular expressions that we've been looking at, but a little bit different. Now, regular languages are closed under this operation. This is great news because this means that I can, without question, take any two regular languages, and I know that when I union them together, that I'm going to get some other regular language. That is a beautiful, powerful thing. Okay, so let's do a couple more proofs. Let's talk about concatenation. Concatenation is when you take all of the strings from one language and you concatenate them with the strings of another language. So in this case, if the strings that are in red here come from kind of language 1, and the strings that are in blue here come from language 2, okay? Concatenation is kind of all of these situations where you have some string from the first language followed by some string in the second language. And so since these are finite, this is a really easy thing to list. The construction method that you would use to kind of start to prove this is you'd put both of these machines together in an M3. That machine M3 has the same start state as M1 does. So we make the start state for M3 be the same as the start state for M1. And then what you do is you take all the accept states from M1 and you attach empty string transitions from those accept states to the start state of M2. And by doing this, anytime you end up in an accept state in M1, you immediately try that same string as if it were beginning a new string in M2. And this kind of guess and check is super amazing and super powerful. And this is kind of our proof method for this situation. So let's go ahead and draw some line here. This is probably not something that comes in as handy as kind of the or expression, but it is useful from time to time to kind of be like, all right, this is how I would construct it if I did know that I had a language followed by another language and they were kind of concatenated together. Sometimes you'll see a little circle for concatenation like this, kind of a center open dot, sometimes not, depending. The last clean operator that we should talk about is the star. And the star is kind of special because in all of these other closure examples that we've been talking about, where regular languages are closed under union, regular languages are closed under concatenation, they have been binary in the sense that you take two languages and you perform this operation on them. Whereas the star is a unary operation. You take one language and you star it. So, for example, if my one language was 0, 1, and I start it, then I could take neither 0 nor 1 if I want, or I can take 0 one time, or I can take 1 one time, or I can take 0 twice, or I can take a 0 once followed by a 1, or I can take a 1 followed by 0, or a 1 followed by 1. And this ends up defining like all binary strings like this, including the empty string. And the star turns out to be something that we can kind of prove in the same sort of construction method. And what we do is we take the original machine M1, we make a new start state inside the new machine M3 that we're going to build. That's this new start state over here labeled with S. We give it an empty string transition to the old start state in M1. And then we take all the accept states in M3 and we attach empty string transitions to that start state. Now, I haven't really in a lot of these construction proofs, I'm doing this kind of quickly. I haven't really given you the meat on how exactly this does prove it. And I haven't kind of probably assured you that that happens and it works. You probably have to try this out and kind of convince yourself. And there probably needs to be a little more explanation kind of saying that this does work. but it does. It's amazing. If you ever find yourself needing to star a language, this is one method that you can use to apply that. But either way, we know that languages are closed under star. So if you know that some other thing is regular and you star it, then you know that that new thing is regular as well, and that is a powerful thing. Complements are also cool. In order to show you a construction of complements, I did a specific example. In this example, I've shown you the string that consists of all odd numbers of zeros. Any binary string that's an odd number of zeros, that's what the left-hand side is. Odd numbers of zeros is over here. Well, let's go, right? And then in order to find its complement, which would be the even numbers of zeros, that's over here on the right, all you have to do is invert all of the accept and reject states. It's kind of beautiful. It's kind of an amazing thing. So just by inverting the accept and reject states, we can show slash prove that regular languages are closed under complementation. So any regular language that you give me, no matter what it is, let's call it L1. We assume it's a regular language. I know that its complement, and often we write that with just a bar over the language. I know that its complement is also regular. It is extremely powerful. The last one that we'll do today is called intersection. It turns out that regular languages are closed under intersection. And what we do in this particular case is kind of this Cartesian product of things. And so what we're going to do is we'll take all of the states and kind of combine them together in order to show that regular languages are closed under intersection. So I've done a brief example here. I'll do one more before I let you go. But in this one, we have that odd number of zeros, finite automata over here on the left. And on the right, I have a finite automata that describes all strings that begin with a 1. And then what I'm going to do is I'm going to combine these together so that in essence, I'm listing all states that are in the Cartesian product of these things, right? And maybe I won't actually touch all of these, but take one state from the left side and one state from the right side. And I'm going to form a new state diagram out of those, kind of like the subset construction, although this is a little bit different. So I'm going to follow the same process. My first state is going to be A and 1. My only accept state in this example is going to be the B2 state, right? Whoops, I didn't mean to erase that. It's going to be the B2 state. This is going to be my start state. And then I'm just going to figure out what all the transitions are. So when I'm in A and I get a 0, I go to B. When I'm in 1 and I get a 0, I go to 3. And so I'll see a transition from A1 to B3, like so, on a 0. Now, I've already done this, so I'm going to kind of show you the end result here. And the end result, let me erase some of my highlights. My end result looks kind of like this, okay? You can see on A1, I get a 0, I end up in B3. Since 3 was this null trap state, I end up being stuck in kind of this trap zone up here. That makes sense because the language we're trying to do is the intersection of these. The intersections of strings that begin with a 1 and have an odd number of zeros must begin with a 1. So if I do end up starting with a 0, I should end up in eternal rejection, right? This is the worst place ever. We don't ever want to end up in eternal rejection. But that's the null state. That's what the null state does for us. We end up over here in the red. If it starts with a 0, we're stuck over there. And then as far as the blue goes, you can see a 1 kind of puts me in this start state. Odd numbers of zeros lead me over here to accept. Even number of zeros take me out. The ones are kind of inconsequential after that first one. And so you can see how it's counting these odds in this loop here, right? That loop is keeping track of our odd numbers of zeros. And that's great because that is the intersection of these two languages. And what we've shown, so we can tell that a language is regular without actually ever knowing what its machine is for sure. We might not know what its machine is. We might not actually even know kind of what the consequences of its language are. But if we can prove some things about the smaller pieces, if I can prove that language 1 is regular and language 2 is regular, then I know some other things. I know L1 intersect L2 is regular. I know L1 union L2 is regular. I know anything in L1 followed by L2 is regular. I know anything in L2 followed by L1 is regular. I know that L1 star is regular. I know L2 star is regular. I know that not L1 is regular, and I know that not L2 is regular. I learn all of these things not by knowing what any of these languages are, but just by knowing that L1 is regular and by knowing that L2 is regular, and that's magical. All right, we're going to stop there. I'm going to let you guys go. 15 minutes is long enough for talking about these properties of regular languages. Um, give some of this a whirl, and we'll see you next time. Have fun. Bye.